Going live now. Hello everyone and welcome to the fifth Open Zemi. Today we are going to have a presentation from Abe Mitsuteru, which is a second year master student in our laboratory. This presentation will be his practice for the master defense next week. He will talk about a simulation, a multi-agent simulation for epidemics simulation. Okay, without further ado, Abe, I pass it for you.
Thank you. Hello, everyone. Today I'm going to present my thesis defense on epidemic simulation. My thesis is titled Epidemic Simulation on Small Community using an agent-based model generated from OpenStreetMap data. Firstly, let's talk about the background of and motivation of our research. As we know, COVID-19 has started a pandemic that spanned more than 2 years. Right now, over 350 million cases and also 5.5 million deaths are reported all around the world. Of course, as we know it, governments try to intervene the spread of the disease with varying success. One thing we observe is that a lot of countries implement the same interventions, such as lockdown, but have a varying result. This different end result between communities might indicate that the effect of behavior of those communities to the spread of the disease. As we know, the different communities adopted a different behavior. For example, different countries have different compliance level regarding wearing masks, and also routine weekly prayers adopted by majority population in some countries, and also different main method of transportation. We believe that studying the behavior of the people and the characteristic of the disease is the key to understand this pandemic. So how can we learn about this pandemic? One way to study epidemic, which is the smaller version of pandemic, is to create a model. A model is a thing we use to follow or imitate something. For example, if we want to study a solar system, we use an orrery, which is the one that you're seeing at the screen right now, which is a model of our solar system. There are many ways to model epidemic, but the most common techniques are compartmental models, neural network models, and also the agent-based models. Each model have their own advantages and downsides, which cause them to serve the different purposes. The first model that I want to talk about is compartmental models. It's a very common model to be used in epidemic modeling. In compartmental models, we divide individuals into several compartments and give transition probability between each compartments. Some notable studies using this model is SER modeling of COVID-19 and dynamic by here. And then the modeling of the early phase of Belgian COVID-19 epidemic using a stochastic compartmental model and studying its implied features by Abrams. The second type of model is a neural network model. The goal of using this model is to predict the number of active cases and also new cases per day. A neural network model is useful when the characteristic of the disease is unknown. The common architecture used in this research is usually a recurrent neural network or a long short-term memory neural network or LSTM. Notable studies using these network models are COVID-19 forecasting using web-based and participatory survey data by Compartmental and also epidemical predictive modeling of COVID-19 infection, development, testing, and implementation on the population of Benelux Union by Sustersik in 2020. So the third model that I want to talk about is the agent-based model. Agent-based model is a computation model that tries to simulate action interaction between agents and environment. The goal of agent-based model is to study the effect of collective behavior of the agents to the environment or other agents. In terms of epidemic agent model, the notable studies in this using this model are analyzing the combined health, social, and economic impact of the coronavirus pandemic using agent-based social simulation by Frank Bicknam, reinforcement learning for optimization of COVID-19 mitigation policies by Farun Kompella, and quantifying the effect of norm of COVID-19 users using an agent-based simulation by Beach. So let's talk about our proposed model. But before that, what do we want from our model? So during the literature study, we found out that most model that do the approach that we want to do usually simulates a hypothetical city or did not use a geolocation accurate infection model. Based on this, we saw a niche that is to be filled, which is we want our model to simulate a real city, have a geolocation accurate infection model, and also can simulate behavior of the people. To fulfill these needs, we choose an agent-based approach. So to answer these needs, we propose a simulator that consists of three main modules: the environment modules, behavior modules, and epidemic modules. We also have a UI modules that help visualize the simulations, such as the one that you are seeing right now on the screen. Let's talk about the environment modules. Environment modules are responsible for providing an environment for the agents to use by using OpenStreetMap data. So our environment module is designed to provide simulation environment that is based on a real city. So that's cover one of our needs. In our environment modules, we divide the buildings into living quarters and also public buildings because we want agents to live in a living quarters and then work at the public buildings, such as office or convenience store for some convenience worker. The second module is the behavior modules. Our behavior module defines how the agent behaves on map, which cover the needs for simulating people's behavior. We divide the agents' activities into three different categories, which is the health-based activities. For example, if they are having a severe symptoms, they will go to hospital and then get hospitalized. And then the scheduled activities, such as the one going to work, because works usually have a schedule, and also a need-based activities to simulate their hunger, for example. So if they're hungry, they can eat at home or eat at a restaurant. Each activity is constructed from two types of action. The first one is idling, which represent their activities inside the building. So if they eat at a restaurant, they will wait for 20 to 30 minutes inside the buildings. And also moving is to get from one building to another building. The third module is the infection module, which defines how the infection spread. Our infection model is similar to a compartmental model. Because we wanted to simulate a geolocation infection, we split the transition between susceptible to expose into four types: at the building, at home, on the road, and off map. Each of these transition, except for the off map, requires agents to be in the same place as the infected agents. And since our infected agents are have each latitude and longitude where they are in, so we could use a geolocations accurate infection model. We also split the infectious compartment to three different compartments, which is the asymptomatic, symptomatics, and severe. This was used by the behavior model to define the agent's behavior, like if they're sick, they go to the hospital. So let's talk about the experiments. We run 4 different experiments using our proposed model. The first one is the effect of vaccination rate to the spread of the disease. The second one is Japanese state of emergency, which is exploring the effect of totally closing restaurant and also reducing work our restaurant. The third one is mass PCR testing. What if what if self-isolation is based on positive tests compared to by symptoms? And lastly, the restaurant closure and replacing the dine-in with the deliveries. For our experiment setting, we simulate areas around the University of Tsukuba. We use 5,000 agents with profession derived from demographic data. When available, or when it's not available, we use assumption based on the building data. In our experiment, we use 4 core CPU and require 4 gigabytes of RAM. The number of cores itself can be edited by using the config file. We simulate 49 days with 3-time repetition to avoid extreme result. Let's talk about the first experiment. So this fascination of effect on the spread of the disease. This study was done actually as the first stage of validation for our model, but we redo it because we got new data. According to WHO, the vaccination only reduced the infection rate by 60% and 40% if it's against Delta strain. This means that the vaccine did not produce perfect immunity against COVID-19. The goal of this experiment is to see what if an outbreak occurred in partially vaccinated population. We simulate for vaccination rate, baseline with no vaccination, vaccination population of 30%, which is represent Japan, 50% to represent USA, and 80% to represent herd immunity. we expect that population with higher vaccination rates will have a lower active and cumulative cases. The cumulative case graph shows that the higher vaccination rate, the lower the total number of cases. What we found interesting is that despite having 80% vaccination rate, the reduction of number of cases is only around 35%. This might indicate that vaccine needs to be combined with other intervention to reduce the number of cases. On the number of active case graph, we saw a significant reduction of 2 based on the vaccination rate. But interestingly, the 80% vaccination rate shows a longer epidemic duration. While this result is less encouraging, it is important to note that our infection rate parameters might be higher than reality, and a lower number of active cases ensures the hospital to provide enough beds for the patients. So let's talk about the second one, Japanese-style state of emergency. In this experiment, we try to simulate the Japanese state of emergency. There are two types of state of emergency. The first one is the total closure of stores, so stores are totally closed. Is applied around April 2020, and also the one that the reduced work hour, which is applied several times, and with the notable one is around Tokyo Olympic. In this state of emergency, with restaurant closed at 8 p.m. and then provide cannot sell alcoholic beverages. So the goal of this experiment is to see how big the reduction of both intervention compared to no intervention scenarios. In these scenarios, we begin simulation without any interventions. Once the number of symptomatics and severe agents reach 150, we start the intervention on the next day. So the graph on the right shows that the active case and cumulative case. In both cases, we could see that a reduction of active cases and also cumulative for both scenarios. But interestingly, the difference between reduced work hour and store closure are pretty similar. This indicates that harsher intervention might have resulted in better infection control. Another interesting thing is that when we compared our result to Kagoshima prefecture infection, we found out that the daily new case in our simulation follows the same trend as the infection of Kagoshima. For example, we see a reduction of number of cases during weekends, and also we see the reductions once the lockdown start, which is around day 8, and then the reduction are fairly similar over time. But while this is good, this indicates that our infection probability is higher compared to the real world. Why? Because we simulate a small areas inside Tsukuba, but we got the same result as a whole prefecture. So the second experiment is the mass PCR testing. And the third experiment, sorry. In this experiment, we try to simulate the search of people taking PCR tests, such as the one we see in South Korea or US. The goal of this test is actually to make people do early self-isolation, so stopping the propagation of the disease to the population. So we wanted to see what happened if people rely on all PCR tests and to see which validity of the PCR test is important. In this experiment, we change the behavior of the agents. So instead of doing self-isolation because of symptoms, we do self-isolation based on positive PCR test result. We simulate 4 different scenarios, which is baseline where nobody took PCR, and then no expiry, 3-day expiry, and 7 days expiry. Interestingly, we observe a higher active case for the no expiry scenario compared to our baseline. On the 7-day expiry scenarios, we see no improvement compared to the baseline. And lastly, when we only saw the reduction of cases on the day 3 expiry scenarios. As previously mentioned, the goal of this test, the PCR tests, are to reduce the infection that come from people who doesn't have symptoms. So as we can see, the infection from the asymptomatics is much more lower compared to base for each of these scenarios. But unexpectedly, there is a massive increase on the symptomatic infection. So we wanted to see where this increase of infection happens. So we realized that there's a lot of infection in the hospital. We realized that this happens because the influx of people taking PCR tests, and also because we use the same infection chance at the hospital compared to other buildings. In reality, hospital should have a better infection measures, which should reduce the chance of infection at the hospital. As the for the experiment 4 is the closing shop and providing with delivery. So in this study, we wanted to see actions taken by non-governmental actors in the pandemic. Recently, due to the social distancing and lockdown, restaurant faces a lot of loss income. So to handle this problem, a large number of restaurants in Indonesia and Vietnam start to shift their business from dining to online deliveries like Uber Eats. In these experiments, we want to see if these changes actually affect the spread of the disease. So in this experiment, we close some businesses and provide their service in form of delivery. In this simulation, agents with low hunger value can order from a restaurant and the food will be delivered to their doorstep by delivery person. We wanted to see how far these changes affect the number of cases compared to no intervention. So in this scenario, we simulate 4 different scenarios. The first one is baseline with no lockdown. The second one is closing restaurant and providing food deliveries. The third one is closing supermarket and providing groceries deliveries. And lastly, we close both and provide everything with delivery. We observe a significant reduction for intervention that target restaurant. For example, the delivery restaurant is here, and also delivery boat is here. But the delivery, interestingly, the intervention that targets supermarkets doesn't show any significant reduction. So the interesting part of this experiment is that the number of infections in most places are relatively the same as the office, university, school, and home and hospital. We see a lower number reduction on the road because people travel less. And also we see a slightly increase on the off-map simulation. Off-map is infection where people live in the simulated areas like in Tsukuba but work in Tokyo. This is because the people that work in Tokyo are exposed all the time. So because they didn't get infected inside the simulated areas, they got infected in Tokyo. That's the main idea. So the reason why targeting supermarket is not as effective as the restaurant is that because the retail have a low in the baseline, have a low number of cases, and also the restaurant have a high number of cases. So of course, by cutting this, definitely the number of infections will decrease by a lot. This is also helped by the fact that the infection at other places like home, school is relatively the same. This indicates the importance of choosing the right place for creating intervention that targets specific places, such as restaurant or supermarket, something like that. So let's go to the discussion. So this study aims to develop an agent-based model that simulates epidemic with geolocation accurate infection model. This was achieved by separating computation into 3 different modules, which is the environment, behavior, and the epidemic modules. So, further study to test how many agents we could simulate might be required because we already use 5,000 agents right now. While we did manage to develop the model, our model have a variety of limitations. There are a lot of missing buildings and information from the OpenStreetMap data, and also due to time limitation, we limit the number of agents in our simulation, which cause a lower number of population density, which might impact how the epidemic growth. Lastly, our epidemic model is relatively a simple model that might not represent what COVID is. So a further study with the help of medical field will definitely improve this issue. So we create a simulator that can simulate the spread of disease within a small community. On the first experiment, we explored the effect of vaccination to the disease spread and found that the number of active cases are reduced despite the vaccine inability to provide perfect immunity. On the second experiment, we explored the effect of Japanese-style state of emergency, and the results indicate similar reduction between total store closure and reduced work hour, which indicates that a harsher interventions might not produce a better result. On the third experiment, we explored the effect of mass PCR testing and found that having longer validity for the PCR result raises the number of cases. On the fourth experiment, we explored the effect of replacing business with deliveries. The result shows that targeting places with high number of infections, such as restaurants, reduce the number of cases better than targeting places with lower numbers, such as supermarket. While our result might not reflect reality, the number of different experiments shown in the proposed model shows the model has potentials and flexible enough to be used as tool for studying pandemics. That is all. That brings us to the end of my presentation. Thank you very much.
Thank you very much, Abe. That was a great presentation. And now we are going to have some questions from first the people in our group. So today we have Anna. Would you like to open up with some questions for Abe or comments? Oh, all right.
Oh, sorry.
Oh, okay. You guys did not hear me. Okay, okay. I was not muted in the stream. So let's go on to questions. Anna, would you like to ask some questions or make some comments for Abe's presentation? Anna, we are not hearing you. All right. I will go briefly. So let's see. Anna. No, Anna, we cannot hear you. Okay, while we wait for Anna to check her microphone, I will move to Ifan. Ifan, would you like to ask some questions or make some comments for Abe's presentation?
Thank you for your presentation, Abe. So my question is, when I listen to the presentation of research on simulation models, I always want to ask, like, how can we ensure the simulation is correct?
Yes, that's a very hard question because a model is actually a model. So it's not going to exactly the same as the one we see before. But the main idea of the agent-based model is actually to expose the dynamics inside inside this complex system, like the how the people behave and the effect of this behavior to the to the disease spread. So while it's hard to validate this whether the prediction is correct or not, but the one thing that the interesting about agent-based model is that we wanted to know what will happen. We could explore what if conditions that we might not have in the real world, and because of this information was explored, we could be more careful when we are making decisions in the future. That's the main idea of this study.
I see. Thank you for your answer.
All right. Oh, yes, we can hear you now, Anna.
Okay. Sorry for earlier.
No worries.
Okay, I have a question like about research in general and a comment about presentation design. Maybe I'll start with presentation comment. I found some slides a bit overwhelmed with text. It was hard to read and also listen to you. And I will send you the numbers of slides that I noticed that. And I think it's better to just, instead of writing full full paragraphs, just do the thesis like points. And about the research, you used a very nice visualization on the map of agent movement and infection. And I think in itself, it has a good science communication value. But maybe you could talk a bit about what are some other advantages of using map information for your simulator.
Well, the most advantageous thing of using map information is that the we could model the agent's behavior basically a little bit more closer to the real world. We could measure the distance of of uh, from their home to their destinations, and that which translate into a duration of travel. And whoever passed or whoever passed with this person on the road, which of course is a exposure duration, which might cause a transmission of disease. But yeah, that's a really very good point. I'll keep it noted.
Okay, thank you.
All right. Thank you very much, Anna. Thank you, Ifan. Next, Jair. Jair, would you like to make some questions or comments for Abe?
Yes. On slide 15, you show the infection model. Why did you choose this one?
So the basic model, because I have limitation in medical knowledge, I choose a simple model, which is the SEIR model, which is only have 4 compartments. But during the development, we see that it is not enough, because we have the exposure types in our simulation are different. We have at the building, at the home, and all of these have different chances. So because of this, we have to modify the SER model. That's why so this is the basic this is a modified SER model that fits better for our simulation. That's the main idea of this, why I choose this model.
I understand. Thank you. I have one more question. It is, how can your research be used, for example, for decision makers? Or should they use? If yes, how can they use those informations?
So how it can be used, definitely. There is still a lot of work to be done until it's be what they call a much more a better model. It needs to be improved some. Like we need to improve more of the buildings informations, and also the population informations for it. Like we need to reduce the basically what we need to do if we want to use this model is to reduce the number of assumptions that we have. By reducing the number of assumptions, we could have a much hopefully a more accurate model of the real world, and maybe expose more issues that might happen if for example, if the government decide on new policies before, so they can test these policies on the simulation before they apply it and then on the real
world. Do we need a very accurate model to be able to draw some conclusions of the dynamics?
I'm not talking about a very accurate model, but maybe it's more like the closest thing that we could produce with the data that we have right now. Because this is currently with all our limitation, this is what we could make. But of course, there's still a lot of things that we can improve on it with more data availability and so, and less assumption because more data we use less assumption. We could make a better. We could see a better dynamics inside the simulation itself.
Mm. Okay, I think I have to think a bit to talk to you more about this. Well, thank you. Thank you very much for the presentation.
Thank you for the question, Jair. I think it's very important to think about what exactly we can or we want to make. So that's definitely something worth keeping in mind when we're talking about models. Okay, next I would like to ask, Hakuro-san, 何か質問がありますか？
すみません。聞こえますか？
聞こえます。
はい。質問はありませんけど、少しコメントがあります。まず、素晴らしい発表ありがとうございます。でも、安倍さん、発表するとき、すごく早口して、なんていうか、早口すぎると、ちょっと分かりづらいので、本当に申し訳ありません。もっとゆっくりした方がいいと思います。そして、すっごく細かいところですが、15ページのタイトルは、Infection Module で、でも、その前、12ページ。
はい、Epidemic Module。
はい、統一した方がいいと思います。それだけです。
ありがとうございます。
なんか白さんなんかいいこと言ったね。確かに僕も後でコメントしようかと思ったんですけど、安倍さんちょっと早口だったんですね。はい。了解です。ありがとうございました。Okay, next, Fabio, do you have any questions or comments for Abe?
Yes. First, thanks for the presentation. And could you go to slide 15, please? Where did you get these transition probabilities?
So this transition probabilities is after we do several trials and errors, and we found that this is the configuration that makes the the wave of infection. Of course, having a higher, slightly lower or slightly higher, but also cause the same of the wave. But this is the one that we see that is kind of similar, especially if I recall correctly, this is similar to what happened in Tokyo during that time.
Okay. And it looks strange that the infection probability on the road, that's our open space, is higher than the probability at buildings.
Oh yeah, sorry. So yeah, the infection probability on the road is actually 30% if you are standing at next to the infected person, but it goes lower once the person is 2 meters away until. So if the person is 2 meters away, it's reduced around 5%. It's linearly reduced based on the distance.
Makes sense. Okay, these were my questions. Thank you.
All right, thank you very much, Fabio. Okay, so finally, from the questions here in the group, I would like to ask Mario. Mario, do you have any questions or comments about Fabio's presentation?
Yes, thanks for your presentation, Abe. It was my first presentation to watch, so it was really interesting. And the question that I want to ask is about if you did any forecast of COVID-19 situation for the middle of this year.
So sorry, can you repeat that? The voice is cut.
Okay, sorry. I wanted to ask you if you did any forecast of COVID-19 situation for the middle of this year.
So our model is not designed for forecasting actually.
Oh, I see.
So usually the forecasting, but it could, but with the current assumption that we have, it's not enough to make a forecasting. So our model was designed to explore weird things that happens inside the simulation. For example, like when we do the PCR test, the massive number of PCR tests, we unexpectedly we see a massive number of infection that happens in hospital. But it should not happen there. So because hospital usually have a better infection control. So what we want this model, using this model, is we try to explore what if condition compared to predict forecasting the number of cases.
I see. Thanks, Abe, for your explanation. Well, that's all. Thanks.
All right. Thank you very much, Mario. And thank you, Abe, for your great presentation today. We don't have any questions from the people in YouTube, unfortunately. So I guess we will finish the talk here. And thanks, everyone, for joining us. Bye-bye.